Hello and welcome. Today we are going to take a closer look at the tiny power plants that provide us with the energy that makes our life possible. Mitochondria. We'll take a look at their origins and how they evolved to the point they are now. But first we have to take a peek at the building blocks of all things on Earth, living and otherwise. The elements. Where do they come from and how did they get here? This is the periodic table of the elements. It is the most common way the elements are ordered. This system, which was first used in 1869 by the Russian chemist Dmitry Mendeleev, groups the elements with similar properties together in so-called blocks. The elements are also presented in increasing atomic number. This means that the further you move to the lower right corner of the table, the more protons the elements will contain. Take hydrogen for example. It only has one proton, so it's positioned in the upper left corner of the periodic table. Now we move to helium. This element has two protons, but note that it's on the other side of the table. This is because helium has other properties. It is a so-called noble gas, where hydrogen is a non-metal. There are 118 elements in the periodic table. Of these elements, only the first 98 can be found naturally on Earth, and only 80 of them are stable. The 18 unstable elements are radioactive, making them decay into lighter elements over various timescales. The 20 elements that don't occur naturally have been produced artificially in man-made nuclear reactions, where in some cases they were only observed in quantities of 1 or 2 atoms. Now that we have some basic understanding of the elements, it's time to take a closer look at where they come from. And again we'll have to start with hydrogen and helium. This is because these two, unlike the other elements, come from the Big Bang. But if that's the case, where do all the others come from? The elements with atomic numbers 3 to 98 are formed in a process called stellar nucleosynthesis. As the name suggests, this process takes place in stars, where hydrogen atoms are fused with other hydrogen atoms to form helium. As the hydrogen in the core of the star runs out, the star will slowly die, turning into a so-called white dwarf star, and the story ends there. But with stars that are about 1.5 times as big as our Sun, the reaction goes on. If one of these massive stars runs out of hydrogen, it will start fusing together helium atoms, creating for example carbon. This process repeats itself, and the core of carbon will start forming even heavier elements like silicon and oxygen. After this process is repeated multiple times, the star ends up with a large core of iron and several layers of other elements. There is an important reason that the last core to be fused is made out of iron. When fusing together iron atoms, it takes in more energy than it provides. This means that when a star has formed a dense core of iron, it loses the outwards pressure of the thermal energy. But gravity is still pushing things inward, so you get a catastrophic collapse of the core of the star. In a matter of seconds, the core will be pushed into a ball thousands of times smaller than the original, and it's the bounce back effect of that collapse that produces a supernova explosion. In this explosion is also where the elements heavier than iron are formed. The shock wave of the bounce back effectively blows up the rest of the star, and the outer layers are shot into space with speeds capable of reaching 30,000 kilometers per second. Now that we have seen how the elements are cooked up, we have one more subject to tackle: mitochondria. Just like the stars provide the Earth with energy, mitochondria provide us with the energy that makes our life possible. Mitochondria are organelles in our cell that give us a form of energy called ATP. They do this through a process called aerobic respiration. In this process, glucose is oxidized to form CO2, water and chemical energy in the form of ATP. It is believed that the early eukaryote cells did not contain mitochondria, but that the environment that these early cells lived in did contain bacteria that were able to perform respiration of sorts. These bacteria were then thought to be implemented in the cell through endocytosis. There are multiple reasons that researchers believe that this is how mitochondria were obtained. First of all, mitochondria have two membranes, one of which is typical for bacteria, and And secondly, mitochondria have their own DNA, making the endosymbiotic hypothesis even more plausible. After the implementation of these bacteria, the evolution to the mitochondria we see now is quite simple. The only thing that really changed is that most of the DNA of the mitochondria was transferred to the nucleus of the host cell, leaving only the DNA that is necessary to form the 13 proteins that it needs for producing energy. And there you have it, a roller coaster ride through supernovas that provide us with the oxygen and other elements that on their turn are used by our mitochondria to produce the energy that Dmitri Mendeleev used to make the periodic table of the elements. You know now how it all comes together, or better still, how it all comes apart.